All right, we're looking at answers for review for test 4. So number 1, let's go over here and look at it. Number 1, we have f of x equals cosine of x minus x. Interval is 0 to 2 pi. We want to find absolute extrema. So we need to take the derivative. Derivative of cosine is negative sine. Derivative of negative x is negative 1. Set that equal to 0 and solve. So we need to know when sine is negative 1. That happens at 3 pi over 2. Since we're finding absolute extrema, that means we need to plug in the endpoints and the critical point back in the original function. So f of 0 is going to give me 1. F of 3 pi over 2 is going to give me negative 3 pi over 2, which is approximately negative 4.712. And f of 2 pi is 1 minus 2 pi, which is approximately negative 5.283. So our smallest value is 1 minus 2 pi, and that occurs at 2 pi. Our biggest value is 1, and that occurs at 0. So there's number 1. All right, number 2. We want the absolute extrema of this, so we need the quotient rule. So we've got the bottom times the derivative of the top minus the top derivative of the bottom over the bottom squared. Clean up the numerator, so I distribute, gives me negative x squared minus 3. Distribute the negative and the 2x gives me a negative 2x plus 2x squared. The positive 2x squared to the negative x squared gives me x squared. I got a negative 2x. I've got a negative 3. Set that equal to 0. Set the top equal to 0. That factors into x minus 3, x plus 1. So we get the x values of 3 and negative 1. Set the bottom equal to 0, x squared plus 3. It's impossible for that thing to equal 0, so we ignore that one. So my critical points are 3 and negative 1. So I plug in my endpoints of negative 2 and 4, and my critical points of negative 1 and 3. So f of negative 2, I got 3/7. F of negative 1, I got 2/4 or 1/2. F of 3, I got negative 2/11 or negative 1.81. And f of 4, I got negative 3/19, which is negative 0.157. So my smallest value is going to be the negative 2/11, which occurs at 3. And my largest value is going to be the 1/2, which occurs at negative 1. All right. Number 3. Find open intervals for which the function is increasing or decreasing. So I need to take the derivative. So that's going to be quotient rule. So bottom derivative of the top minus the top derivative of the bottom over the bottom squared. Notice that both of these have a 2x in it. So I factored the 2x out. That left me with x squared plus 4 and the minus x squared. These x squareds cancel. Leaves me with 4 times 2x, which gives me 8x. Set that equal to 0 as you see here. Set the top equal to 0, gives me 0. Set the bottom equal to 0. It's impossible for that thing to give me 0, so that is not a critical point. My only critical point is 0. Anytime I'm doing a sine line, remember you need to plug that into the derivative. So the bottom, I think we talked about this one in class, the bottom is always going to be positive, so all I care about is the top. So something on the left of 0 is going to make my numerator negative, so that's why I'm negative. Something on the right of 0 is going to make my numerator positive, so that's positive. So we're going to be decreasing on the left, we're going to be increasing on the right. So increasing when x is greater than 0 because f prime is positive, decreasing when x is less than 0 because f prime is negative. I think I saw some of you put 0 to infinity right here for this, which is fine, and negative infinity to 0 right there, which is fine as well. Next one, an equation of the line tangent to this at the point of inflection is, so this is one we did in class as well. So first thing I have to do is find the point of inflection, which we get from the second derivative. So I do the first derivative, which is here. I do the second derivative, which is here. I set that equal to 0 and solve, which gives me x equals negative 1. Now, in this example, I went ahead and showed that it's actual point of inflection because my signs do have to change. But I really didn't have to because I have to have a point of inflection, so I knew negative 1 had to be a point of inflection. Once I do that, since it's a point of inflection, I need to get my slope To get the slope, you plug into the derivative. So I plug -1 in, and I plug -1 in, and that gives me a slope of -3. I also need I do need a y value, but this is what we talked about in class. I only have one answer that has a slope of -3, so we can stop there and see that my answer has to be B. All right, 5, we're looking at concave up. So to get concavity, we got to have the second derivative. So here's my first derivative, there's my second derivative. I set it equal to 0. So from the 60x, I'm going to get 0. From the x squared minus 2, I'm going to get plus and minus the square root of 2. I put it on a sine line. I plug into my second derivative, which is here. So we have a negative, a positive, a negative, and a positive. We're wanting concave up, so that means I'm interested in where my sine line is positive. So between negative square root of 2 and 0, and bigger than the square root of 2. So that answer is B. So my answer is B. 6, we did. Oh, no, we didn't. So 6, we want to know when we have a relative maximum. So to get a relative maximum, I got to go to the first derivative. This requires product rule. So first times the derivative of the second plus the second times the derivative of the first. Both of these have an x minus 3 in it, so I take an x minus 3. From this, if I take the x minus 3 out, that leaves me with 2 and x minus 2, which gives me the 2x minus 4. Over here, if I take an x minus 3 out, that leaves me with an x minus 3. 2x and the x give me 3x. -4 and -3 gives me 7. So set this equal to 0. I'm going to get x minus 3 equals 0, which produces the 3. I'm going to get 3x minus 7 equals 0, which produces the 7/3. Sine line, I plug back into my derivative. 0 is over here, so if I plug 0 in, I get a negative and a negative, which produces a positive. In here, it's going to be something, let's see, this would be 2.3. So 2.5. So 2.5 is going to make this negative. 2.5 is going to make this positive, which produces a negative. Plug in 4, I get a positive and a positive, so I'm positive. So relative max, my derivative has to change from positive to negative, so it changes from positive to negative at 7/3. So that's why my answer is 7/3. All right, so then we have the table problem. So A equals f of 5 minus 3x. So we take the derivative, which is here. We want to figure out if it's a point or a critical point at 1. So that means I need to plug 1 in. So 5 minus 3 times 1 produces a 2. I need f prime of 2, which is 0. 0 times -3 gives me 0. So since my derivative at 1 is 0, that means yes, it is a critical point. Then to determine if it's a max or a min or neither, I need to plug into the second derivative. So I take the second derivative. My second derivative ends up giving me this. I plug in my 1, so that's going to be f double prime of 2. So f double prime of 2 is -2. So I have -2 times 9, which produces a -18. So that tells me I have a relative max at x equals 1 because my second derivative at 1 is less than 0. Because if my second derivative is less than 0, that means we're concave down. A critical point that's concave down is a max. A critical point that's concave up is a minimum. Question 8. So we have the derivative graph shown. Which one of these could be the answer? So -2, my derivative changes from negative to positive. So that means I've got to have a minimum there. And 2, I've got to have a maximum there because my derivative changes from positive to negative. So I need a minimum at -2, a maximum at 2. So nothing there, nothing there. Not what I want, not what I want. There's my answer. Minimum at -2, maximum at 2. So that's why we like E. Relative extrema on 9. Let's go find that problem. Oh, looks like it just died on me. So pull that back up. All right. Relative extrema, so I need my derivative. This is the quotient rule. So bottom, derivative of the top. minus the top derivative of the bottom all over the bottom squared. X plus 4 to the third squared gives me x plus 4 to the sixth. X plus 4 squared here, x plus 4 to the third there, so I'm going to take that out. So that leaves me with an x plus 4 times 2 here, which gives me the 2x plus 8. I take it out here, that leaves me with 2x and 3, which gives me the 6x. This and this reduce to give me an x plus 4 to the fourth. In here, I've got a 2x and a negative 6x, which gives me a negative 4x plus 8. Set that equal to 0. Set the top equal to 0, which gives me 2. I set the bottom equal to 0, which gives me negative 4. Notice that I said it's not a critical point. Remember, if you get a potential critical point from the denominator of the derivative, you have to check it and make sure it doesn't cause you issues back in the original. If I plug negative 4 back in the original, it makes my original undefined. So if it makes the derivative undefined and the original undefined, it's not a critical point. But you still want to go ahead and put it on your sign line just in case, or just so you can see what's positive and what's negative. So I put negative 4 on there. I know it's not a critical point, but it's there. I put 2 on there. 2 is a critical point. So all I really care about is what's going on the left of 2 and the right of 2. So left of 2 is going to be 0. So I plug 0 in. My denominator is always going to be 0 because I have an even exponent. Or sorry, my denominator is always going to be positive because I have an even exponent. On the top, if I put a 0 there, that's going to make it positive. So I'm positive here. I plug in 3. 3 here is going to make my top negative. So that's negative. My derivative changes from positive to negative. So that means f has a relative max at x equals 2. And in this case, I went ahead and found the y value, which is 1/54th. Because f prime changes from positive to negative. Remember, if you want to get the y value, you plug the x value back into the original. So if you plug 2 in here, you get the 1/54th. All right, and that's what I've got there. This is the one I had screwed up originally. I went back and changed all the ones to a 6. So I'm looking at f. I want to get the order of f, f prime, and f double prime. And we're interested at 6. So f is going to be 0. Since f is increasing at 6, that means f prime is positive. And since f is concave down at 6, that means f double prime is going to be negative. So f double prime is negative, f of 6 is 0, f prime of 6 is positive. So that's how we get our order. All right, graph of f prime is given. What are the critical points of f? So that means I'm interested in where f touches the x-axis or is undefined. I mean, f prime touches the x-axis or is undefined. So it touches the x-axis at b, d, and f. So critical points are b, d, and f because f prime is 0. Next one, we want the relative extrema of f. So that means f prime must change signs from negative to positive or vice versa. So right here, we're changing from negative to positive, so I have a minimum. I also change from negative to positive here, which also gives me a minimum. So b and f are minimums. As I stated here, b and f are minimums because f prime changes from negative to positive. At d, f prime changes from positive to negative, so that means we have a relative max because f prime changes from positive to negative. Point of inflection. Point of inflection occurs when the derivative changes from increasing to decreasing or vice versa. So that's going to happen right here at C. My derivative changes from increasing to decreasing, so that's why I have a point of inflection at C. And at E is my other one, and that one is because f prime changes from decreasing to increasing. 14, we want to know where f is decreasing. So f is decreasing wherever f prime is negative. So f prime is negative right here from A to B and right here from D to F. So that's why we are decreasing. 15, I originally had this answer wrong. I think I had right there, I had B and it should be A to C. I was looking at Michaela's and Michaela had it right and I didn't. So I made that change there. So f is going to be concave up. We're looking for concave up wherever the derivative is increasing. So we're increasing from A to C, and we're also increasing from E to G. So f is concave up from A to C and E to G because f prime is increasing. 16, how many critical points does the function f of x equals x plus 2 to the fifth times x minus 3 to the fourth have? Let me go find this on this one. There it is. So this is going to require the product rule. So I have the first times the derivative of the second plus the second times the derivative of the first. So I have an x plus 2 here and an x plus 2 there. This is x plus 2 to the fourth. This is x plus 2 to the fifth. So that means I can take out an x plus 2 to the fourth. I have an x minus 3 here and x minus 3 there. This one's cubed. This one's to the fourth. So I can take out an x minus 3 cubed. Right here, if I take that out and that's going to leave me with 4 times x plus 2, which is where I got the 4x plus 8. Over here, I'm going to be left with an x minus 3 and a 5. So that's how I get 5x minus 15. And 4x plus 5x should be 9x. I don't know why it says 11x there. And then negative 7. It doesn't affect how many critical points I have. So if I set this equal to 0 and solve, I'm going to get a critical point for this piece, a critical point for that piece, and a critical point for that piece. So that's why my answer is 3. 17, we want to know for what values is this increasing. So we want the derivative. So I'm going to have to do the product rule with this piece and then just take the derivative of that piece. So first times derivative of the second plus the second times derivative of the first, and then minus the derivative of this thing is going to be that. All right, I've got an e to the negative x there, I've got an e to the negative x there, and I have an e to the negative x there, so I factor that out. It leaves me with a negative x squared, leaves me with a 2x, and leaves me with a positive 3. I don't want my squared term to be negative, so I went ahead and factored the negative out and put it there. So that turns the negative x squared into a positive x squared, turns the 2x into a negative 2x, turns the 3 into a negative 3. Factor that into x minus 3, x plus 1. Remember, you can never get a 0 from an e piece or from an e. X minus 3 is going to give me 3. X plus 1 is going to give me negative 1. So I plug all those in, zeros in here. So 0 is going to give me a positive, a negative, and a negative. So a positive, a negative, and a negative is a positive. Plug in 4, positive, positive, negative. So positive, positive, negative is negative. Over here, negative 2, negative, 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 which gives me a negative. We want to know when it's increasing. So that means we're looking for the positive section, which is between negative 1 and 3. So between negative 1 and 3. 18, let G, or let, it should say G. I need to go back and fix that. That should say G. So we have G of 6 equals negative 2, G prime of 6 equals 0, and G double prime of 6 equals 5. What occurs in the graph of G at the point 6, negative 2? A maximum, a minimum, or not enough information? So a max or min has to occur whenever I have a critical point. This right here tells me we have a critical point because my derivative equals 0. And if I look at the second derivative is positive. So I'm concave up. And if I have a critical point where I'm concave up, then that means I've got a minimum. And it's because G double prime of 6 is positive. So if I want a relative extrema, I need to be... my derivative needs to be 0, and then I determine whether or not my second derivative is positive or negative, and that tells me if I have a minimum or a maximum. All right, last one, second derivative test. I'm not sure I've got this one worked out because I think I added this later. Yep, I don't have it worked out. So on this one, you need to take the first derivative, set it equal to 0, and get your critical point, which it looks like is 1, and then you take the second derivative, and then you plug 1 in. So when I do that, I plug 1 in, and 1 in the second derivative is positive, so that means we're concave up, which means I have a minimum. All right, so there's a quick run through of the answers to review for test 4.